Hello and welcome to the Keon's Lab 1000 subscribers special. And a huge thank you to everybody who helped get the channel all the way up to this point. 1000 subscribers is a pretty big milestone for this channel. So in order to show my appreciation for all of the support and the rapid growth of this channel, I am going to make this probably one of the coolest videos you have ever seen relating to lithium-ion hybrid supercapacitors and super high power jet turbine fans, such as these ones over here. And by high power, I'm talking like 390 watts high power. And I'm going to do this by making the very first video on the internet at the time of recording, and I can say this confidently, to not only present this brand new generation of lithium-ion hybrid supercapacitors, featuring higher voltages per cell and higher capacities than any lithium hybrid or lithium-ion supercapacitor that you have ever seen in any video. And when I say big, I'm talking kilofarads big, because I feel that it's only right to celebrate a 1000 subscriber special with a 1000 farad supercapacitor. But didn't I already make a video on these things? Well, yeah, I did. But because of how special this video is going to be, I'm not just going to be presenting these supercapacitors on their own, because I already did that kind of in my part 1 of how supercapacitors, the lithium ones, work. Oh no, in this video, what I'm going to be doing is using these brand new types of supercapacitors, which again, you have not seen anywhere else in video form. We are going to be making either a 12 or 16 volt lithium-ion supercapacitor pack with the goal of delivering up to 40 amps so that we can actually power these super powerful jet turbine fans at full power without the restriction of the 10 amp current limits on the power supplies I have here. Since the jet turbine fans, which I now have 3 of now, are actually rated to pull up to 25 amps, 390 watts. And 25 amps is 2.5 times the current limit on these power supplies, which makes these jet fans the perfect candidates for testing out and experimenting with this brand new type of lithium-ion energy storage solution. So join me on what will be a very exciting series of videos where we begin exploring and experimenting with this brand new type of supercapacitor technology. Welcome to Keon's Lab, and I really hope you enjoy the video. So with the intro out of the way, let's start by briefly going over how and why I plan to do this using the supercapacitors instead of standard lithium-ion batteries. Before also briefly covering what makes these jet turbine fans so special for all of the new viewers. And then we're going to go ahead and start with the actual build of the supercapacitor pack itself and then test out the fans. Because while I could easily overcome the problem of the 10 amp current limit on the power supplies by just making a massive lithium-ion battery power pack, I have the holders for the 18650s. I could easily do that if I wanted to, but that's not the point of this video or of this channel really. Because of course it's going to work if I make a big enough battery pack. Realistically, here I have one right here. I could even just use a sealed lead acid battery like this. 12 volts, 4.5 amp hours. I could just easily do that and not have to do any of the work with this brand new technology. But again, that's not what this channel or this video is about. What I'm really interested in seeing is how these super high current discharge lithium-ion hybrid supercapacitors perform when put into unique high power, high current situations like this. So a few weeks ago, while browsing on AliExpress for BLDC motors, I came across something that immediately caught my eye, simply because of how cool it looked. An in-runner brushless DC jet turbine fan. And these specific jet turbine fans are quite unique because while I had seen listings for similar or basically almost identical looking jet fans as these ones, most of them for some weird reason required hundreds of volts to run, with one example I very clearly remember requiring upwards of 300 volts. And not only that, but it didn't have any proper documentation in the product description, and it didn't even come with an ESC. It was just a termination of wires like this. So while I did also take notice of those two, I didn't really pay much mind to them because 300 volts is kind of not really what I'm going for with my projects. So imagine how surprised I was when I looked in the product description for these jet turbine fans. I came to realize that these are basically custom modified BLDC jet fan and ESC combos. And I really need to iterate how cool that is, because apparently these used to be of the 300 volt or the super high voltage kind, where the vendors had actually opened up the motor module, like the brushless in-runner motor inside of here. They had opened it up and unwound all of the stator coils and rewound it with the proper gauge of wire and the proper number of turns and everything, managed to close it back up and basically make it look like it was untouched. And not only that, they took a custom programmable ESC or electronic speed controller and programmed it so that it could control this fan just like a standard BLDC motor with an ESC, and have it consume up to 25 amps, 390 watts. As soon as I saw that it was up to 25 amps current draw, 390 watts, I knew that would exceed the power ratings of both of my power supplies, which would give me the perfect excuse to put together a 12-volt supercapacitor pack and use it to test out with these jet fans. And because it is 12 volts, which is quite a versatile voltage, it can be used with quite a lot of other stuff too. So hopefully that wasn't too boring, because now we can start with the actual project itself. Let's build a lithium supercapacitor powered jet turbine fan. Now wouldn't that be an awesome video title? So in front of me here, I have all the materials needed to construct a 12-volt supercapacitor pack. And before quickly going over what each of these materials are and why I chose these specific ones, I should also mention that the method that we're going to be using to put these together is one that I came up with myself. I'm not saying no one else can do it, I'm just saying that it's the first time I've seen supercapacitors be connected in this way. So now let's get into why I chose what I chose in order to make this capacitor bank. Because the goal of this is not just to make something that is functional, it's to make something that can deliver peak performance and not have any bottlenecks due to the actual connectors or wires being used, and of course something that is safe to use. So in order to choose the appropriate materials for this build, I had to take into consideration not only the specifications of the capacitors themselves, but also the power requirements of what I'm trying to be running with it, which in this case is going to be the jet turbine fans, as well as many other things in the future. So the voltage and capacitance of each one of these cells, probably as you may have seen, is 4 volts and 1100 farads, or 1.1 kilofarads. And the operating and maximum current ratings for the cell, according to the manufacturer datasheet, is a recommended operating current of 6 amps per cell, with a maximum current rating of 40 amps per cell, which is great news because 40 amps is 1.6 times the 25 amp current maximum of the jet fan. And the fact that each one of these is 4 volts makes it very convenient for making packs of 8 volts, 12 volts, 16 volts, and so on. So in this case, we're only going to be needing 3. So these are going to be in a 3S configuration, meaning 3 in series and none in parallel. And because they are supercapacitors, once they are put into series, it's not actually going to be an 1100 farad 12 volt bank, it's going to be a 366.6 farad 12 volt bank. But the amount of energy that's being stored remains the same. So these are called WAGO connectors, also known as lever nuts, I believe. And looking on the side of the WAGO connectors here, we can see printed are 2 pieces of very critical information. One, the gauge of wire that can fit in here, both the thinnest and the thickest. And 2, the maximum current that can be tolerated by these. With an added benefit of using genuine WAGO connectors being that they are manufactured of fire retardant plastic, meaning that they are supposed to be able to extinguish themselves should they catch fire in 10 seconds. There was actually a name for the fireproof rating or something. I'm going to put that here. And not only that, the second reason I chose the WAGO connectors, well, there's 2 more reasons actually. One, I didn't want to permanently solder these capacitors onto anything. I've seen some capacitor banks using the EDLC type that directly solder them onto a PCB, and that's not really something that I like the idea of too much. Because one, it's not repairable, so if a capacitor goes bad, it's going to be pretty difficult to try to replace that thing. And I also just don't like the idea of having to put a soldering iron directly up to these leads. I know it should be fine, but I like to keep heat away from my capacitors and batteries as much as possible. And now for the third and probably most convenient reason that I picked these is because when you put these side by side, it sort of forms like a grid. You can see it's like a perfect grid. And this makes it quite easy to plan out how you're going to wire out wire up the supercapacitor bank. And it just comes down to the fact that you can sort of give it like a coordinate system like I did here, where I gave letters that weren't associated with either the capacitors or the, can't remember what the other one was, but I went from E to J because I was using 1, 2, 3. So I was using 6 LEGO connectors, and the diagram you're looking at here is for the 12 volt one we're going to be making right now. Actually, before I begin explaining all of this, let's just go over the connectors and the polyimide tape. So because I'm not planning to install this capacitor bank anywhere permanently, and it's going to have to be recharged by plugging it and unplugging it, I wanted to pick a power connector that can not only be more than enough to handle the current, but that would also be not annoying to have to take out every time. And that would also not wear out with repeated insertions and deinsertions. if that's what it's called. So here I have two examples of some high current power connectors. These are XT60 power connectors. They're super cheap. It's like 99 cents for 10 pairs of them, or at least it used to be about 2 years ago when I got these. And they're basically nothing more than two banana plugs, the same type that would go into those connectors on the power supplies, just of a thicker caliber basically, put into a plastic shell housing. And these are quite common on things like 3D printers, for example. That's the only place I've seen them so far. However, I do believe they're used in quite a few other electronics. I mean, they have to be. They can't only be used for 3D printers. They're quite difficult to take apart. So for something that's meant to be plugged and unplugged repeatedly, having to do this with that amount of force really is not the optimal solution to me. Which brings me to the solution that I settled on, which is aviation connectors. This is a 20mm, it's called a GX20 aviation connector. I'm not quite sure why they are called aviation connectors. One answer I found on Google was that apparently it's as simple as they're used in aviation and military applications, which again would make sense because these seem to be quite reliable. And I do know that giant versions of these are used like in factories and stuff. And I actually didn't know that these aviation connectors were even a thing that you could buy until I actually went looking for some kind of 3-pin or 2-pin connector that was similar to an XLR microphone cable that I have. So at first I was searching for XLR type power connectors, and this was the default thing that came up every time. So I explored them a little bit and realized that these are actually extremely convenient and useful ways of connecting high power devices. So it makes it very, very easy to just have this side be connected to the actual capacitor bank, and this side be connected to your charger or your load or whatever. And then when you want to plug it in, you just... Oh yeah, and here's another thing. It's tabbed, so you can't put it in the wrong way. It can only go in one orientation. So when it's in, you screw it in like that, and now it can't come out at all, no matter how much you pull on it. And that's really another added benefit of these aviation connectors. So that is what I'm going to be going with today. So right before we begin assembling the pack itself, let's just go over the last final two materials. So this is polyimide tape, and it is the standard type of tape that you would see on lithium polymer batteries, for example. It's capable of handling quite high temperatures. I don't remember right now by heart, so I'll write it down. I'll put it on screen here. But this tape is usually used also on things like 3D printers, like on the hot end. It's used for, like, people use it for putting it on modules before soldering because the soldering iron cannot melt it, or most soldering irons at your normal soldering temperatures cannot melt it. So it's really, really a very convenient type of tape. It is also electronically insulating and quite easy to work with as far as cutting it goes, because you can just put a little slit with a blade and it usually goes in a straight line. And then the final material here is 12 gauge silicone wire. So if we see, it's printed on the side here. So 12 AWG, so 12 gauge, 200 degrees Celsius is the maximum temperature that this wire can handle. And silicone wire is the type of wire that should always be used when doing high power applications like this, with an added benefit being that it is extremely flexible. So even with the massive 12 gauge wire here, look how thick the leads are in here. If I can focus on that, very, very thick leads, but it's still very flexible because of the silicone, which, as you're going to see, is going to make putting the pack together very flushly, very, very easy. So now let's get on to the actual assembly of the power pack. So in order to properly understand this drawing that I've made, I should probably put the WAGO connectors in the proper orientation according to this, so you can properly have it in context. So I'm assuming that this drawing might look complicated or confusing, but it's really not, and it's really going to make more sense. And you're going to see how intuitive it is once I actually put the WAGO connectors side by side and explain the coordinate system. And again, this is a method I came up with because I wanted to make sure that I wasn't stitching wires through in between the power leads. I wanted to do it the proper way. So putting a sticky note here upside down so I can stick the WAGO connectors on. You may notice that the drawing here is basically depicting the WAGO connectors themselves. So there is 1, 2, 3, 4 of the 3-pin WAGO connectors and 2 of the 2-pin WAGO connectors. So 1, 2, 3, and then 2 of these. Or 3, it's 4. 4 of the 3-pin connectors. And the way they're going to be put together is going to be like this, into what I'm calling like blocks. So you have like these blocks of the WAGO connectors, each one consisting in this case of one capacitor and power leads connecting them together. So I'm going to put these on the sticky note here in accordance with the drawing. Okay, so I've arranged the WAGO connectors in the proper orientation in accordance to the drawing, and I've also labeled out the coordinate system right beside the WAGO connectors. So now it should be quite easy to explain how this is going to work. By making a coordinate system, it allows me to make like a legend here where I assign what I call an ID from and then ID to, and that's just some arbitrary thing I picked. I didn't know what to put there, but it's as simple as a to and from connection with a little connection symbol here saying that what type of connection it is. So when I put a dot, it means that it's where a capacitor lead goes. And then when I put to, it just means that there is a wire that's actually going into the tab. So let me start with demonstrating how we're going to be doing this. The legend is overdefined. So for example, when we have F2 to G2, if we find G2, it says G2 to F2. And I did that on purpose so that if I got something wrong, I would catch it on the second time, because this is really something you do not want to mess up. So we're going to have C1, capacitor 1, C2, capacitor 2, C3, capacitor 3. So starting with C1. So C1 negative goes to E3 and C1 positive goes to F3. And let's see if that corresponds. So simulating, putting it in here. And see the negative is in E3, and then the positive is in F3. So then putting it into the next one, simulating capacitor number 2, and they're going to be the negatives are going to be facing each other like that. So G3 should be capacitor 2 negative, and H3 should be capacitor 2 positive. So let's check. G3 is capacitor 2 negative, yep. And then H3 is capacitor 2 positive. And the dots denote that it is the connection of the lead here and not like a bridge wire. Then for capacitor 3 negative should be in the pin I3, and then capacitor 3 positive in J3. So let's see, I3 is capacitor 3 negative, yep. And then J3 is capacitor 3 positive, and that corresponds. So now we go to the wiring. So everything that doesn't have the dot. So E2 goes to the in and out negative pin of the aviation connector. So E2 would be here, and that's why it's only a 2-pin connector. So that goes to the master in and out power cable. F1 is not connected, so it's not used. F2 goes to G2, so we're going to put a wire from here, F2 to G2 right here. And that's going to be connecting the positive of capacitor 1 to the negative of capacitor 2. Okay, now where were we? H2 goes to I2, so H2 goes to I2. It's a pretty simple construction. That's another wire going from the positive of capacitor 2 to the negative of capacitor 3, with finally J2 being the in and out positive of the capacitor bank, also going to the aviation connector. So we're going to have the main power cables coming out from here, bridge wires going from here to here, here to here, and then these ones remaining not connected so that later they can be used to check the individual cell voltage and maybe at some point implement a balancing system. So with that explained, we can now actually begin assembling, because I kind of needed to refresh myself on it too, just to make sure I don't get anything wrong. And the reason I do this is so that everything can be wired beforehand, checked for the proper connection beforehand, so making sure there's no bad connections with a multimeter, and only then inserting the capacitors. And it also helps that I can put polyimide tape on the bottom of the blocks. I call each one of these blocks. So I can put tape on the bottom of them before the tabs are closed, and that prevents everything from just going all over the place, because the wires are going to be very short pieces to keep the resistance low, and that's going to kind of make a bit of spring force. So I like to put tape, polyimide tape on the bottom, and then when everything is closed up, I tape it all together, and then I put tape on the capacitors just to keep them together and prevent them from bending or splitting apart. And sometimes I put like a shield tape over the exposed pins. So because of how simple of a construction this is going to be, we're only going to need 2 short pieces of 12 gauge wire as the connections from here to here and from here to here, and then 2 longer pieces for the main power cables. So getting all this stuff out of the way, we're going to start building this thing. So I'm going to start by cutting 2 relatively short pieces of 12 gauge silicone wire, and the color here doesn't really matter because we're just connecting the positives to the negatives, so it really doesn't matter. So I'm just going to use a red wire, So it's going to be maybe that long, just enough to be able to go in a complete bend like that and not be too springy to prevent it from going together smoothly. So I think maybe that should be a good length. So I'm going to cut that and strip both ends, and maybe a little bit longer because the ends do go into the WAGO connectors. So accounting for that and the length that I'm going to strip it off at, maybe about that long. And I'm going to make 2 of these. So I'm going to cut 2 of these of the same length, strip the ends, and then come back. Okay, so with both wires stripped now and twisted on the ends, and I cut them a little bit longer so that I can trim it down and restrip it just to get the perfect fit. Let's do a test fit here. So bending it in half, it seems to be about right. Yeah, that seems good. Okay, so let's go back to the legend here. The first connection is F2 to G2. So F2 to G2. So before doing that, I'm going to actually take all of these off, flip them upside down, and put polyimide tape to secure the bottom. This will make sure the coordinates don't get all messed up once the wires are in place and trying to move everything. Okay, so now I can put polyimide tape on the bottom and on the sides, and then flip it back around, open all the tabs, and start building. So getting these lined up. Like this. I'm gonna bring it on the side here, and then use the X-Acto knife to slit the extra part off. Okay, so I'm gonna put a slit here and close that on there. Next, I am going to trim this part off. Okay, so that part is trimmed off. Now I'm going to cut this part out, like that. Then I'm just gonna fold this part over, and then just slit the sides like the other one. So 1 and 2. I'm just gonna fold these over, like that. Nice, okay. So that's 1 block, and I'm gonna repeat this for all of the other ones, and then come back when it's done. Okay, so with all the blocks now taped up, and the wires now stripped, get everything into frame. So now just to orient these according to the drawing, so like this. So everything is according to the drawing now. So now we can keep the drawing close by and begin opening all of these tabs up. Oh yeah, and that's why I didn't use the letters A, B, and C, because I was using that to refer to the blocks. So block A, block B, block C. So block B and block C. 1, 2, 3, 4, 5. So again, aligning it up with the sketch. Now we can start putting in our wires. So double checking here, F2 goes to G2, inserting the wire into F2, making sure it reaches the actual engagement point, and closing the clamp, pre-bending it a little bit to make sure it holds its shape. So putting that wire in, making sure nothing, see, something's sticking out on the side here. So take that out, retwist it, putting it in, and closing that tab. So now we have F2 to G2. And the camera stopped recording there because for some reason, Apple makes it so that the iPhone has to have the charging cable unplugged and replugged after rebooting. So even though I had plugged in the power cable while I was recording, it kind of died. But anyways, back to the build. So we had F2 to G2, and then G2 to F2. We only have 2 wires to connect. So again, so F2 to G2 is just a redundant one. It's the same thing that we have here. So we're gonna go to the next one, which is H2 to I2. E, F, G, H. So H2 to I2, the middle one in there. Putting this into H2, like that. That's in, then bending the wire a little bit. And now we go to I2. That's the J, and this is I, so I2, right in the middle. Like the symbol for elemental iodine. Okay, so now we have our wires connected. So I'm just going to strain them or like bend them even more. Like that. Okay, and when all of these tabs are closed, it's all going to come together beautifully. Now it's time to connect the power connectors. So I have already pre-soldered a 2-pin aviation connector for the test build I did of this, which is honestly a good thing because the video is getting kind of long, I think. Okay, so I have my pre-soldered GX20 2-pin aviation connector here, and it is using 14 gauge wires since I had soldered this before I had the idea of the supercapacitor bank. Well, before I got to making it, but 14 gauge should be fine for doing this test, especially because it is silicone wire and it's not that long of a length. So you can see there's polyimide around here, and I'm gonna put heat shrink on here later too. You can see I have the heat shrink here. So basically taking this apart. This side, the female side, is going to be on the load or charger side. And the reason for that is because it's the side that's most prone to shorting. So if you have a piece of metal that gets stuck here, that would easily short it out. But on the male side here, it would take a lot more of a deliberate effort to try and short out those two things. This aviation connector has obviously already been checked to make sure that the red pin actually does go to the red pin. Since you can see there's numbers here, but I still always double check because that's what you do. But I have the 2-pin aviation connector here, and it's time to connect it up to our bank before connecting the capacitors. So male side for the power bank, J2 was in-out positive, and then E2 was in-out negative. So putting E2 to the in-out like that, and then J2 was in-out positive. Making sure the wires are twisted. The positive goes into J2, the first port. Putting it in all the way, closing it. So now everything is wired up and ready for the capacitors to be inserted. So you can see it's coming together quite nicely. So E3 is C1 negative and F3 is C1 positive, which would correspond to this, like that. So I'm going to take the protective shielding off. I'm going to make sure to try to get it standing up as straight as possible. So again, double checking, triple checking the polarity, inserting, and one side is longer than the other one. However, that is fine because both sides do reach to the bus bar inside of the WAGO connector. So making sure this is standing up as close to 90 degrees as possible. Like that. Snap it closed. Like that. So C1 is now installed. So now on to C2. And because all the negatives are going to be in the same orientation, it's going to be quite easy, but still double checking. So the rest is pretty straightforward. Just taking the things off of here, making sure they're evenly spaced out here. Okay. It keeps going out of focus. So installing capacitor 2, closing the tab on H3. Now closing the tab on G3. Like that. So capacitor 2 is now installed. And for capacitor number 3, things off, and it's pretty straight on there. E, F, G, H, I. So I3 is negative. Now I wish I could get a better angle, but I need to make sure that they go in straight. And then closing that one. Like that. So all 3 capacitors are now installed. And the remaining tabs can be closed because they're unused. Now we can see how everything is going to fit together beautifully. Look at that. Nice. So now polyimide taping all of the blocks together. Making sure everything is securely on here. And then using the X-Acto knife, an actual X-Acto knife, to make the little slits so we can fold it like a present. So 1, 2, and 3. So 1, 2, and 3. And now for the final side. Pushing this against the spring force of the wires, making sure it's aligned on the bottom, while applying the tension, and then using this, make sure everything is on securely. So now we finally have our completed 12-volt supercapacitor bank, all assembled, all taped together, with our aviation connector. So now, right after I check how much free space I have so it doesn't cut off again, I am going to start checking the voltage and we're going to charge this up and power the jet fan. Because again, this is the 1000 subscriber special, so we're doing two things in one video. Okay, so with the multimeter out now, we can start, first of all, keeping this disconnected, connecting up the leads. Like that. Making sure they're far apart. Each cell, I think, was charged to about 3.6 volts, so it should be about 11 point something volts. Haven't charged this up yet. 10.82 volts. So let's unplug, get the power supply connected, and see how many watts it draws to charge up to 12 volts. So the leads are in, but before connecting the actual capacitor bank, we're going to double check the output voltage to make sure it's exactly or as close to 12.00 volts as possible. Because each cell has a nominal voltage of 4 volts, 4.0, so the nominal voltage of this capacitor bank is exactly 12.0 volts. So the power supply is set to 12.00 volts, but it is probably going to give a little bit over that. So 12.02, that should be fine. Let's try 11.99. 11.98 goes to 12.00. So attaching the negative to the negative, pushing on it, the positive to the positive, and pushing on the leads. Let's connect this power bank to the power supply, screw in the aviation connector. Nice. Set this standing up. The timer is here, it's at 0, and the current limit is set to a 10 amp maximum, so it's plenty to work with. So beginning charging in 3, 2, 1, go. 54 watts. 49. It's pulling a decent amount, 45 watts. It's not even getting warm. Look at that nice little graph forming. Little curve. This is a programmable power supply, so I should have connected it to the computer so I could actually... Or actually no, because the software is horrible for it. So it actually would cut off the graph as it proceeded. So it wouldn't even let me get a full readout. But for discharge testing, this thing is going to give us a very, very, very nice discharge curve. So 32 watts, it's been 1 minute and 15 seconds. Making sure to be exactly at the 12.00 or 11.99 volt mark. You don't want to leave it floating, like connected to the charger and be overvolted. A tiny amount, I'm sure would be fine. I just like to keep all of my cells healthy. Unlike, again, Apple, when it comes to their Macbooks, who really doesn't care about how hot the device gets. When I'm editing my videos, it gets 98 to 101 degrees Celsius, according to a software I have that reads out the internal temperature sensor readings. And I have screenshots of it too. I'm actually working on a device to solve that problem because it gets to the point where the MacBook overheats so much that just putting your finger on it makes it speed up. Like when I'm in Premiere Pro, it starts going choppy because it's 98, 99 degrees Celsius and it's throttling the processor and the GPU speed. So we're at 15 watts now. So I'm basically making a product. It's going to be an actual product at some point. That's going to be the ultimate MacBook cooling dock to just permanently eliminate this problem and do what Apple should have done. Instead, they just keep taking the fans out and putting stronger processors inside. Innovation. 13 watts. Like, I don't get why they take the fan out of the laptop. It makes no sense. And I've found a direct correlation between the heat and the performance of the laptop, which is obvious. So like I have this tiny little ceramic tile that I put the laptop on when it starts overheating when I'm editing the video. And as soon as I put it on that ceramic tile, the temperature is dropped to like 86 degrees Celsius. And what do you know? It starts speeding up again. And I actually used my thermal camera to locate exactly where it's getting the hottest and it's right in the center part for the M1 MacBook Air. It's right in the middle part of the speaker bar. I think that's where the logic board is or something. And it really doesn't help they're using the aluminum chassis like a heatsink, but then they have the batteries housed, like sandwiched between the two layers of the aluminum chassis. Very smart design, Apple, very smart. 8 watts. So I'm going to cut the video here and come back when it is right about 50 milliamps draw, or 75 even. Oh, and actually right before I do that, what I like to also do is put the multimeter on so I can monitor what I call the offline pack voltage, because I'm also working on making the first, as far as I can tell, the first dedicated, what I'm calling the CMS, capacitor management system, for these capacitors. Because just as Tom Stanton said in his, I keep mentioning him, in his airplane video with the supercapacitor, there is no dedicated charging system for these. And I intend to be the first to make one. Not only make one, but bring it to market maybe at some point. Hopefully, if my YouTube channel is successful. Okay, so connecting the multimeter for a live monitoring of this. And the capacitors are a tiny, tiny bit warm, but nothing significant at all. Again, they are brand new cells. So you can see it's 12 volts because it's charging. And I'm not going to do the off and on because it's going to ruin the timing. You know what, a couple seconds won't matter. So if I turn off the charging right now, you can see it drops like 11.93, 11.92. So I'm going to turn it back on. And based on many, many, many tests I've done with this over over a year, once this gets to about 50 milliamps draw, it should be holding at about 11.97 to 11.985 volts. And then if you let it go all the way down to 25 milliamps draw or below, it should be almost exactly 12 volts. And I have also found that in the bulk charging phase, like when you're still at like 10 volts, you could overvolt it by like 10 millivolts, 12 millivolts, and it'll speed up the charging, but you always want to go back down to the exact 12.00 as you're approaching as you start getting closer to the actual nominal voltage. So I'm going to cut the video here and come back when it is almost done charging. So I think I'm going to disconnect it here because when I turn the power supply off, it's holding right about 11.99, 11.98 volts. It's close enough, because it's going to take forever for it to go all the way to the full nominal voltage. So once that gets to about 75 milliamps of power draw, we're going to disconnect it, and the leads that are coming out of the Aviation connector are going to be run into these 2-pin WAGO connectors, and then those are going to be connected to the jet fan, specifically the ESC power lines of the jet fan, which I think I'm going to strip a little bit more of just to get a better connection. Make sure it reaches. Okay, so now we're going to disconnect everything. But first, making sure to actually disconnect the Aviation connector. So disconnecting the power bank before touching any of the main connections. And this is why I really like the Aviation connectors. So with that disconnected, it's now safe to work with this. Okay, so we are now finally ready with our newly made 12-volt lithium hybrid supercapacitor power bank to connect to the ESC of this jet fan and see what it can do. So the ESC negative, in and close. And then for the positive, and it is connected. Okay, so now we finally have the jet fan with the ESC that is connected to the Aviation connector plug. And we have our 12-volt supercapacitor bank. Okay, so making sure the PWM controller is all the way down so it doesn't spin up right away. And the instant I connect this, it should make a beeping noise, which is the ESC preparing the motor. Ready? I'm gonna 3, 2, 1. Wow. Works perfectly so far. So the ESC is now armed and ready to go. So let's put these here. And I just don't know how to demonstrate how much power this is going to give out. So it's going to be taking air in from here and sending it out from here. So I'm going to put up a couple of heat sinks and show how powerful it is that I can move the heat sinks. Okay, so now let's put this on here, put that like about here. So the ESC is obviously still armed, the LED is on. Let me angle it in such a way so that you can see the turbine spinning and the heat sinks moving. So you can see the turbine, and in 3, let me aim it directly at the heat sinks there. Imagine putting like a crosshair thing in. Okay, so I'm aiming it right at about this area. So all of the power that you're about to witness is coming from these 3 supercapacitor cells. So there's nothing on in 3, 2, 1. Now that's a lot of power. Certainly was not that powerful with the normal power supply. It threw that heatsink off. So let me put this on the bigger heatsink. Let's see if I can throw that one off. And in 3, 2, 1. Oh my gosh. In my last video where I had the turbine connected to the 10 amp power supply, it was barely enough to just move this a tiny bit. This just threw that heatsink off. And this is a big heatsink. Look at the thickness of that base plate there. So I'm going to take this copper bar. It's a 3mm thick copper bar, 10 centimeters by 4 centimeters, and I'm going to put that on top of here. Add a little bit of weight. Let's see if it'll still be able to flip it over. I don't think it will. It'll probably just rotate it, but let's see. Unfortunately, I don't have an ammeter that can actually measure how much current this is giving out, because obviously the multimeters are limited to 10 amps, and this is giving way more than 10 amps. So I need to get one of those Hall effect. Like, I have the module, I just haven't set it up yet. And in 3, 2, 1. I think it was about to flip it over. Capacitors, tiny bit warm, but nothing significant at all. Okay, in 3, 2, 1. I could move the heatsink with the air. Or actually, let me try it with a smaller piece of copper. This is my calipers have actually broken, so I don't really know the thickness of this. And now let's try to knock it over. In 3, 2, 1. It fell. Nice. So now I'm going to disconnect the turbine from the capacitors and show how it compares when connected to the power supply to show how much more powerful these capacitors are. And then we're also going to check the voltage on here to see how much it's dropped. Okay, so with the ESC now connected to the power supply and not the supercapacitors, giving it the same 11.98 volts and blowing at the heatsink with no copper on it, let's see if we can knock this one down. So we're turning the power on, it should make the beeping again. So it's ready. So I'm going to put it in the same angle as before. And in 3, 2, 1. So I was about to knock it over there, but you can see nowhere near as violent as with the capacitors. Now for the copper round thing on it, it's probably barely even going to move it. So let's see, 3, 2, 1. So you can see the difference. It's still very powerful, but nothing compared to the supercapacitors. And then put the copper bar on it. Three, two, one. And nothing. Okay, so ESC is now connected to the Aviation connector here. So just to prove that there's no power coming from the power supply, I'm going to turn the power supply off. Copper is still on the heatsink. It's out of frame. So capacitor power again. In 3, 2, 1. So a noticeable difference, but I think they're going down in voltage a little bit because when you put the capacitors in series, while these are 1100 farads, right now it's a 366.6 farad bank. So at some point, I'm going to connect the second one of these that I made, which actually looks kind of nicer to be honest, and put them in parallel like this. So then it's going to be a 733.2 farad 12 volt supercapacitor bank. You know, maybe I could do that right now, but I would rather wait. So now let's disconnect the capacitor bank and check the voltage on it. Okay, so it's connected, but let's check the voltage on these. It's at 11.22, so that's actually not bad. 11.22 volts. So let's do a couple more bursts with the fan and then check the charge current or the wattage. And keep in mind, this doesn't even have a nozzle on it. It's just purely an air duct. Okay, so the ESC is back with its connection to the Aviation connector. And let's connect these capacitors up one more time. So I'm going to do this one test, and then I'm going to switch over to the thermal camera. Okay, in 3, 2, 1. This thing is making a lot of thrust. Let's see how much it can... Well, it's probably going to go on a curve, but... Yeah. It's trying to lift off. I am not exaggerating this. This is actually how much thrust it's making. And I'm being careful not to be too loose on it because you really don't want to get a finger in there. That thing is making a lot of power. Capacitors are a little bit warmer, so now let's switch over to the FLIR camera. And the FLIR camera, like, I think it's the reflection of the infrared. It sort of shifts the image over, so it's pointing at what would be the center, the middle of the capacitor. But it looks like it's offset, but it's really not. And the frame rate is low because it's doing a thermal imaging thing, but anyways, let's see how much it heats up. I'm just going to blow the fan in a random direction. See how there's like a thing coming off of the side here? It's offset the thermal image or whatever, so I'm going to point it at the middle of the hologram basically. It's still over 3 times cooler than the MacBook Air when working with Premiere Pro. And we're pulling a lot more current than a MacBook. Anyways, so in 3, 2, 1. And it makes so much thrust, it's actually kind of difficult to hold back. And they're a little bit more warm now. Okay, so it's about 40 degrees Celsius. Not too bad actually, considering the fact that the milliamp hour equivalent of these cells is about 500 milliamp hours. It's advertised as 450, but I ran the discharge test and it gave about 500. So considering the C rate that's coming out of here, 40 degrees is really not bad. So let's check the voltage now. So let's go back to the normal camera. Disconnecting the power bank. Let's get the aviation connector out. And we have 8.82 volts. Okay, and to find out the minimum voltage for this, each cell on its own, the 4-volt ones, should not go below 2.5 volts. So 2.5 times 3, so 7.5 volts is our minimum voltage here, so it's quite decent. So to find out how much free space we have here, I'll do 8.82 minus 7.75. We have 1.32 volts left, which is a lot, but I really want to see how much current and wattage it draws when it's plugged in to charge. But with the power supply now connected to the aviation connector with 11.98 volts like before, let's plug in the capacitor bank. And the aviation connector has a notch on it, so you can't put it in the wrong way. Okay, so the timer is at 0, wattage 0, 11.98 volts, in 3, 2, 1. Wow, 110 watts. 100. This thing is charging right now at 100 watts. 115. I can give it a little bit more current actually. I can go right up to 10.1. 120 watts. I did not expect that. 120, 118 watts. This is insane. Just want to make sure they don't get too warm. So yeah, nothing concerning at all in terms of the temperature. And the connectors aren't warm at all, of course. That's why we chose the WAGO connectors. After 6 minutes and 40 seconds of charging, it's now down to 8 watts, 600 milliamps of current draw. And let me connect the multimeter for a offline reading. So disconnecting the power, which is going to disconnect the timer, which is currently at 7 minutes and 25 seconds. So it's at 11.92 volts. So it was at 8 point something volts before, and after 7 minutes and 25 seconds of charging, it is now back up to 11.91 volts. So turning on the power again, drawing 7 watts, 6.5. Okay, so with the aviation connector now connected back to the ESC, so no power is coming from the supply anymore. All the power is going to be coming from the capacitors again. And we were at 11.96 volts when I disconnected it. So reconnecting, and we were at 11.96 volts on the supercapacitor bank, but since it was plugged in and then it cut off, the video cut off, we can assume that it's about like 11.95, 11.94. So the arrow is going to be going that way. So in 3, 2, 1. I could sense the amount of thrust going down a little bit, but you could see how violently it was pushing this heatsink. Capacitors are like about 40 degrees, just relative to what it was before on the FLIR camera. Really not that hot, to be honest. Okay, so now let's check the voltage. Because we didn't even give it a full charge cycle. We just cut it off at about 550 milliamps. Just above 40 degrees Celsius. So the voltage is not bad, 9.8 volts. These are actually performing pretty well for just being a non-parallel configuration, just 1S. What am I saying? 3S. It's a 3S configuration. 3S, 3 in series. So now let's charge it again and see how much current it pulls. I'm just gonna put it on the ceramic tile just to let it cool down a little bit. Because while it's not hot, when we were charging it and it was pulling 100 watts, it was getting kind of warm. And again, these are rated to be able to handle way more than this. I just really like to keep my batteries and capacitors healthy. Okay, so with the power supply now reconnected to the Aviation connector, I can plug this in. Okay, so in 3, 2, 1, start charging. Oh my god, 115 watts. This is insane. This is actually crazy. They're not even that warm. Just put a little ceramic under it, and I have a little invention I've made that's gonna really make this a non-issue. So I think about here is where I'm going to end the video, because I don't think many people are interested in just watching something charge. It's like watching water boil, basically. So while I am gonna wait until it goes down to about like maybe 100 milliamps of power draw, this is basically going to be the end of the video, and therefore the end of the Keon's Lab 1000 subscriber special. So if this video was cool and you want to see more stuff like this, because I've got plenty more stuff similar and even cooler up my sleeve. So if you want to see stuff similar to this, make sure to like and subscribe to the channel. And thank you so much for not only getting the channel up to 1,000, it's actually over that now. It's like 1,140 subscribers, I believe, the last I checked. So thank you for getting the channel up to 1,140 subscribers. Hopefully it'll keep growing. And also make sure to let me know in the comments if this was indeed one of the coolest videos you have seen relating to lithium, it's out of frame, lithium-ion hybrid supercapacitors and BLDC jet turbine fans. And remember, these capacitors, all of these, my channel is the first place on the internet to show them in video form. And I'm proud to be the one to present them. And thank you for watching the 1000 subscribers special on Keon's Lab. So 75 milliamps, and yeah, okay. So I'll see you in the next video. Bye.